Alrighty, good morning everybody. Welcome back to Alpha 1. Plan for today is we're going to finish off our discussion from last class of optimization in Standard 17. And then our next office hours are on Monday at 11 and at 2. As far as homework goes, we're going to have a quiz Monday over Standard 17. And there will be a homework 20 that will be due on Wednesday on optimization. I say will be because I still need to actually post it. But that'll be posted later today. And also don't forget you have a homework due tonight. Quizzes from last class I still haven't finished grading. I'll get those back to you on Monday. My apologies on their tardiness. Does anybody have any questions or comments before we get started for today? So, here's one thing I want to talk about. I want to talk about the final exam. Specifically, when is the final exam going to be offered? Because we have two choices. First of all, first option is on Monday of finals week at 8 a.m. Your second choice, Saturday at 8 a.m. These are not my choices of times. Basically, why we have a choice of two times is the registrar assigns like a different final exam time for each kind of hour time slot. This class technically takes up two different time slots, the 8 a.m. Monday, Wednesday, Friday time, and the 9 a.m. Monday, Wednesday, Friday time. So we can kind of have the option of choosing the final exam to be at either of those times. And I wanted to see what you all thought. So this is the first day of finals, this is the last day of finals at 8 a.m. You know, everybody's favorite times to take exams.
What's the date? Oh, jeez. What day is Monday?
The day before Tuesday.
Hey.
So this is the 6th, and this would be
12.
I think it's the 11th. Monday plus 5 equals Saturday, 6 plus 5 equals 11.
I have a strong preference for Monday.
Yes.
I feel Saturday.
No.
All right, someone tells me, Josh, you're going to be outvoted, but let's put it to a vote. All those in favor of Monday? Sorry, Josh, you lose.
It's always about you, man.
Okay, so
You can take it.
all right, so we have a winner. So final exam is the first final exam slot, Monday the 6th at 8 a.m. You'll have 2 hours. I'll probably let you stay a little longer. Final exam, just so you know, will be just like the midterms. They'll have every standard on it. Get as many masteries as you can. It's your last chance. Oh, also for the final, you are allowed to bring in 2 sheets of paper, front and back, whatever you want written on it. Then, I know grammar. And yeah, that's all I have to say about the final right now. But yeah, plan on this, and if this doesn't fit into your schedule for any reason, let me know, and we can probably work something out. What do mathematical mermaids always wear? They tend to wear algae bras. Algebra. Took a minute on that one. Alrighty, so last class we had talked about the optimization process looking at how do we optimize the volume of a Coke can given a fixed surface area. And if you recall, we had kind of a sequence of steps for determining, or for going through the process. Where our first step is draw a picture. Depending on the problem, it might not always make sense to draw a picture. A lot of them will. Like I think the last one in the packet asks about car rentals, and that one probably doesn't make much sense to draw a picture on. But if you can draw a picture, help you understand what's going on. Bless you. Step 2 is going to be to find formulas for the given information. Step 3 was to put the expression you want to optimize in terms of one variable. So if you remember last time, we had a volume of a can that we wanted to maximize, but volume was in terms of two variables, the radius of the top and bottom circles and the height of the can. And so to get that in terms of one variable, we needed to use the information we were given from the surface area formula to find, what was it, H in terms of R, so that we could write our volume formula just in terms of R. And then step 4 is once you get to do that, find your critical points. And step 5 is prove you found a max or min, depending on what the question asks for. So what I want to spend today's class doing is looking at a few more examples of the sort of problem we worked on last time. And this time we'll go through them maybe a little bit more quickly just to see what's going on. So to start with, I'm going to be on page 3 in the packet, where no self-respecting Calc 1 class would be complete without an example of trying to fence something off on a farm. So here's the scoop. We have a rectangular plot that's going to be fenced off with one side along a river where no fence is needed. So we want to fence off a rectangle, and it's going to be along a river. So here's going to be our river. It's a polluted river, so the fish are dead. And we are going to fence off a section of land. I don't know why I felt the need to kill the fish. I guess I'm in a bad mood this morning. So the question is, if we have 100 feet of fencing, what are the dimensions of the maximum area that we can possibly fence off? So we're given 100 feet of fencing to work with. In order to make this sort of rectangular shape where we have 3 sides of fencing, and how big of an area can we make inside of those 3 sides? So I already drew a picture. So we want to somehow account for finding formulas for what we're given. So first of all, what kind of are going to be our variables that we should probably include in our picture to indicate the different dimensions of the fenced-in area? Yeah, Josh?
Your 2 sides and then the one on top.
Yeah, basically, what's the size of these 2 sides? I'll call them, let's say H for height. And then since we have a rectangle, we know the left and right sides are going to have to be the same. And then the top, I don't know, W for width. So I think everything can be written now in terms of W and H. So first of all, what's going to be the function we want to maximize in this problem? Rachel? Okay, yeah, it asks us to maximize the given area. Let's write it as A, I guess. And in terms of the variables H and W that were given, what's the area going to be? W times H. Yeah, I like it. So W times H is going to be the function that we want to try and maximize. And we're also given some other information, specifically that we have 100 feet of fencing to work with. How can we write an equation involving H and W that'll somehow account for having 100 feet of fencing to work with? Avery?
2H plus W equals 100.
Okay, so you're basically just adding up this section of fence plus this section of fence plus this section of fence. The lengths of each of those should add up to 100. Yeah, we could say that the perimeter of the fenced-in area, so to speak, not including this bottom side because that's just poisonous river, is going to be given by H plus W plus H, or 2H plus W, and that's going to come out to 100 feet of fencing. So I think that's all the information we're given. We have 100 feet of fencing, that should be 2H plus W. The function we want to maximize is our area function, which is W times H. So this one we're given is 100, and this one is the one we want to try and maximize here. So can we skip right to step 4 and take our area function and go ahead and differentiate? Cecilia, why not?
Because we have two different variables.
Gadzooks. Right now, our area function is not just in terms of a single variable. It has a W in it and it has an H in it. So we can't just say differentiate that right away because there's multiple variables. So we need to somehow get our area function down so that we can write it in terms of a single variable. Josh, any ideas on how we could do that?
You could manipulate the perimeter equation to something like W equals 100 minus 2H, and then plug that in.
Ooh, okay. So you want to solve the perimeter equation that we have for W? Sure. W equals 100 minus 2H. That's just what one I did. You could also solve, I think it also wouldn't be too much harder to solve that for H. You'd get something like H equals 50 minus 1/2 W. And then plug this back in up here. Sounds reasonable to me. Okay, so our area then is going to be, it's going to be what, Josh?
It'll be 100 minus 2H times H.
100 minus 2H times H. And because I think it'll be easier to work with if we multiply that out.
100H minus H squared.
100H minus 2H squared. I like it.
I just have a question. I guess I'm confused. I'm probably thinking about it the wrong way. But for W equals 100 times minus 2H, if we take 100 and subtract like the height off of both sides, wouldn't that give us the length of both the top and the bottom?
That's true. If the whole perimeter should come out to 100, and we're subtracting off the left and right sides, we should then get what's left in the top and bottom.
Okay.
Yeah, but since we didn't need any fence along the river, we could really say that the bottom edge is really using just 0 feet of fencing. So we're really just left with the top. That might, that's a good thought for maybe the next example. But everyone on board so far? So based on what Josh suggested, we're able to take the function we want to maximize, area equals width times height, and by substituting in this w equals 100 minus 2h expression, we're able to write our area now just in terms of a single variable, namely h. That area came out to 100h minus 2h squared. So if we wanted to label kind of each of our steps, I would say picture up there is step 1. This stuff was step 2 right here. And then step 3 was getting area in terms of a single variable. You don't have to label these 1, 2, 3, 4, 5. I'm doing it for this example just to make sure everybody's clear on which part of the process each of these steps corresponds to. But if you're doing this on like a quiz or an exam or something, you don't need to label 1, 2, 3, etc. Okay, so what's next? We have area in terms of a single variable, 100h minus 2h squared. We have something we want to maximize, and it's just in terms of a single variable. See it?
You want to differentiate?
Groovy. Okay, so if we differentiate, take a prime of h, what's that going to give us?
100 minus 4h.
100 minus 4h. Yep. So that's something we can differentiate just with the power rule here. What do we want to do with our derivative? You want to find our critical points. First of all, are there any values of h where a prime is undefined? Don't think so. We can plug in any number we want for h, and it'll always come out to something that makes sense. So I think our only critical points that we would get come from setting this equal to 0. How do I solve this equation in terms of h?
Subtract 100 from both sides and divide by -4.
Oh man, you want to make everything. Didn't want to add 4h to both sides, keep everything positive. I'm going to introduce some negativity to this class.
Here's the problem.
Okay, which will give us what for h?
25.
25. 25 feet. Yeah. So basically, we're seeing that that this side length should be 25 feet. This side should be 25 feet. So that tells us kind of our critical point for how to maximize the area with this height. What would the width have to be in this case?
50,
How'd you get 50?
because you have 2 H's, so that's 50 feet. And then what's left over is 50.
Okay, so basically you're using the 2h plus w equals 100 formula? Yeah. The way I'm going to do it is, since we already have an exact formula for w in terms of h, I'm just going to use that and say w is going to be 100 minus 2 times 25, which will be 100 minus 50, which is 58. So we found a single critical point, a single value of h that will make the derivative of our area function come out to 0. So what's our last step going to be in this process?
Prove we found a max.
Let's prove we found a max. So this is our step 4 here. And for step 5, we need to actually show that we just maximize the area instead of, say, minimizing it. How do we do that? Rachel, what's our procedure for showing that we found a maximum here?
Can plug in a point to the left and
see if what's positive or negative. The output for the function which function, A or A prime? Yeah, we need to check A prime on either side of our critical points and see if we can use the first derivative test to show us we found a maximum. Sorry to keep putting you on the spot there, but something that's easy to make a mistake on in this sort of problem is to plug values into A rather than A prime, which will give you the wrong ideas. So I only have a single critical point here, which means I think this will be not too bad. You know, A prime at 25 is 0, so we just need to pick any point to the left and any point to the right of 25. What would be a point to the left of 25 that we could check? Izzy?
1.
Okay, let's check 1. That's actually a pretty nice one to check. It'd be nicer than 24 or something. So if we take A prime of 1, we'll get 100 minus 4 times 1. That smells positive to me. What are you going to suggest, Josh?
I was gonna say 24.
Nice. All right, Josh, give me a number to the right of 25 that we can check.
25.2.
All right, does anybody else want to give me a point to the right of 25 that we can check? Technically, that does work, but I just don't want to.
25.3.
All right, guys, I have an idea. Let's check A prime of 30.
I got you, Josh.
Let's see if you got this quiz on Monday. All right, Zach, 100 minus 4 times 25. You know, I should have just gone with your idea and then made you do the calculation. That's what I should have done. We take 100 minus 4 times 30. Is that going to be positive or negative?
Negative.
It's going to be 100 minus 120, which is going to be negative. Stop talking in the front row. So A prime is going from positive to negative at h equals 25. So what does that tell us?
It's a maximum,
What type of maximum?
an absolute maximum for our interval.
Ooh, absolute maximum. How do we know it's absolute?
Well, because it's positive to the left everywhere, 25, and negative to the right everywhere. 25.
Yeah, since A prime is always positive to the left, meaning our area function is always increasing to the left of 25, and A prime is always negative to the right, meaning area is always decreasing to the right, by the first derivative test variant we talked about last class, not only do we have a local maximum for area function at h equals 25, we also have an absolute maximum as well. Let me write that down, and then I'll do that. So we can say since A prime of h is positive for all h less than 25, and A prime of h is negative for all h greater than 25, our area function has an absolute max at h equals 25. And I think we are done. We've found the dimensions that'll maximize the area inside of our fencing, and we've shown that that gives us an absolute maximum for our area function. Yes, Fidik, sir.
I was wondering, I know we know it's like absolute with this one because it's kind of a simple equation, so we know it's just like a single curve. But when our equations start looking more complicated, how do we know if it's absolute or if it's just local?
So if we were to end up in a situation like, let's say, we found two critical points, and I don't know, it was something like plus, minus, plus. If we were in a situation like that, so that would indicate our function does something like would argue, I don't think we have an absolute max or an absolute min in a scenario like this.
So it's only defined by as long as we find all the critical points, we'll know how the function behaves.
Yeah, as long as we find our critical points and if we, make our little number line like this and check points on either side. Basically, what's going to end up happening is most of the problems, like for basically anything I would give you on a quiz from the standard, if I ask you for an absolute max or min, there will be one, and the first derivative test will work, which usually means there's only one critical point. Or maybe there'll be multiple critical points, but one of them's negative, and it doesn't make sense to talk about negative values in the context of the problem. So we could still use the test to find an absolute max, which I think is what happened in our Coke can example last time, where we said, oh, R could be 1 or -1, and since it doesn't make sense to have a negative radius, we just said, oh, 1's the only one we care about.
Do we not need to include the actual area in our answer?
It depends on what the question's asking for. I think if I ask what are the dimensions of the maximum area, that just means what are W and H. But if I were to ask you what is the maximum area that could be enclosed, then you would actually need to find the area. How would we find that?
You would just multiply the width by the height.
Yeah, so if we wanted to, we could say something like, oh, then the area is going to be 25 times 50, which is 1250 square feet. Yes. It's the biggest area we can enclose within this space. Yeah, whether or not you need to actually compute that or just say, oh, here's the H and W that will give us our maximum area, depends on what the question is asking. Danielle, did you have a question?
Yeah, this might be obvious, but why are we able to plug the H that we got from taking the derivative into the W formula that's not a derivative?
Oh, good question. I think that's because in step 3, when we were able to write our area function in terms of a single variable, what we basically showed is that in order for our perimeter condition to hold, W has to be equal to 100 minus 2H in every circumstance, no matter what H is, in order to end up with using 100 feet of fencing, W has to be equal to 100 minus 2H. I guess if we wanted to, we could not use the whole 100 feet of fencing, but that would certainly not give us a maximum area then. And so when we saw that our area function has a critical point at 25 feet, since W is always just going to be this this expression in terms of H, no matter what value we're plugging in for H, whether it's at a critical point or any other point in our area function, we could just still use this formula, which works not only for our critical points, but for any other points in an area formula as well. Does that make sense?
Yeah.
Cool. Good question. I'm glad you asked. Any other questions or comments about this problem? So just like last time, we had a picture. We found formulas for the information that we were given. All right, fine. I'll give you one live fish still. Fish are not extinct in the river. He's happy his family is dead. That's a sadistic fish right there. We found formulas for function we want to maximize or minimize, and whatever else the problem gave us, in this case the perimeter of our fenced-in area. We use this perimeter formula to write the area function just in terms of a single variable by solving for one variable in terms of the other and substituting that in. Step 4 is basically, steps 4 and 5 are the same sorts of things we did in standard 15, where we find our critical points by taking the derivative, setting it equal to 0. And then in step 5, we use first derivative test to prove we had an absolute maximum for our function. I'm not going to ask you a question on a quiz that says something like, find the absolute maximum, and there isn't one. That would be, let's use class appropriate language, a jerk move. If I ask you to find an absolute max or min for something, then there's going to be one. Here's a bonus joke of the day. A mathematician is asked to fence in the maximum possible area using 4 feet of fencing. And so what the mathematician did is they said, all right, here's the mathematician. I'm going to fence in a 2 by 2 by 2 square area and declare that the inside of the fence is everywhere out here. And so if they're on the outside of the fence, they have fenced in the maximum possible area, which is everything outside of this little area. Okay, no, don't actually do that here. All right, with that, I have a question I want you all to work on. So if you flip to the next page of the packet, there's a very similar sort of problem, except this time we're going to ditch the river and assume we do have, like what Benedict wanted earlier, I think, the fourth side is also going to be fenced in, using that same 100 feet of fencing. And so now if we remove the river and require that all 4 sides are going to get fenced in, what I want you all to figure out is what are going to be the dimensions of the new maximum area we can get using that 100 feet of fencing. So as always, you're welcome to work with your neighbors and or ask me questions. And we'll come back together in a few minutes to see what you all find if you do the same process again, but with 4 fenced in sides rather than just the 3. I'll take one of that up here.
A TikTok video about someone leaving a fence school bathroom.
I'm sorry I asked.
I'm sorry.
Yeah, you should be.
I'm done. Yep.
Yeah.
Mine's half. I don't know right now.
So you just do your whole equation here where it's 2h plus
It'll be 2.
2 what?
It'll be 2H.
2h plus 2w.
Yeah, so it's
And then you just solve for w. It's just like the same thing, but then you just divide everything by 2.
I'm teaching dogs about
So
it.
you have w becomes 50 minus h. And then
We
you
didn't
plug
grade
that.
books many.
Great books.
That sounds like a lie.
You
Right
solve
now?
your perimeter equation, w equals that, plug it back into your area.
It's not great.
And
books.
then you derive. You know what.
I'm also best at talking
Not anymore.
And then
Calvert.
Easier to solve for one or another.
He's really easy.
Like in the last problem,
Me
it was
too.
slightly easier to solve for W in terms of.
Easier than Moss.
But in the last
He
class,
actually
it was a lot
Because
easier.
Moss
like-
was certain grades.
In this one, dimension, just this
How
easy.
do
you know this guy's
I
easier?
know.
Because
And
everyone's
in that case, it doesn't.
You're getting moss.
Yes.
I shook my head no. I think yes, I shook my head no. I didn't.
H minus H squared.
It should end up, you should end up with the exact same
I hear
solution.
Roger is boring.
So in this case, if you solve for W in
Albert's
terms of
interesting.
H, write,
It's a
write
square
everything in
base.
terms of
Factor
H.
it in.
I think I
and
care
derivative,
about
you get the
being
same W and H critical point value.
Okay, yeah.
Solve for 0, and you
Okay.
should get H equals 25, plug
Here's
that
the
back
thing.
in.
Did the same thing with all the other variables.
I'm so mad at your mic.
Sorry, I don't know who
You text me that, I want to shoot.
Think of them that way if it helps you, but not graphically. Typically,
Chill.
so like in the last problem, I would say that once we got to that forward, H was like our X value, our input to the area
So
function, and then our output.
I gotta get it
was,
trimmed up a little bit.
W times H.
Gotcha.
And that would sort of be like what our Y value is.
So it just like sticks out on the sides like this too much.
And then it's gonna be the same line.
Does Maddie like it?
She doesn't care. I'm pretty sure she'd rather just have my normal hair.
Yeah, for like the highest stuff.
For the highest stuff, not horizontally, so if I tried to find like an absolute max.
This is who I am.
Heard Jack lost last night.
You know, like walking, and there's
Yeah, so
Jack
here
has
we can
like-
sort of think about this as being our H axis.
Like, oh.
This being for the last problem, and this is
That's
telling
a little weird.
I'm like,
what area
I could've waited
is.
till we were all.
But had I not what you did
The door was
to
closed.
W, would have gotten the same thing.
It would have been a different
Trying so
looking
hard, I
graph
started
slightly.
like,
Yes.
So
Like,
then
it would have been a W equals 50, for instance, instead of
Have you
25.
seen the video?
But it would have, it would have corresponded to
You
the
went in
exact
there?
same critical point.
I went in there and I saw Nick after
Or
30
W
minutes and I wanted to do that video, but I
H
just
equals
stopped.
25.
So I left.
Those always correspond to the same thing.
So it really doesn't
I
matter.
couldn't, I just
It
couldn't
doesn't really.
stop laughing.
Other than the fact that
I
sometimes it's
messed up.
easier to solve for one in terms of the other. And,
I'm afraid
in that
he
case, I would say
he
solve.
like come out and just swallow each other.
Good question.
No problem.
No.
What are you talking about? Is that what, bro, is this?
You're already under the next one.
Yeah, I know, I did, I got what you got.
Oh, lucky you.
Oh, we gotta go?
You gotta go.
Fox was square.
Two. Yeah, which I hate. I don't know why I hate that. Okay, and then,
There's 3 variables.
Sorry, I already gave you this one yesterday.
oh, no, yeah, you're fine. So x squared times by all of that.
Okay, let's come back together to talk about this one. So it looks like most of you have a good start on this. So up around.
No.
So
One variable, buddy.
what's our function we want to maximize here? It's area. What's our area? Hey, how about that? Same as last time. Adding in an extra section of fence doesn't change the area that's enclosed. It's still just going to be width times height. How about the perimeter? Someone other than Josh. That's it?
2L plus 2W.
2L plus 2W. Throwing a new variable in at me, huh?
Oh, yeah, sorry.
For the record, it doesn't matter. As long as you're consistent about it, it doesn't matter what you name your variables. Since I already wrote H's out in my picture, I'm going to stick with H. But if you wanted to do it with L's instead, that's equally valid. So yeah, so now our perimeter is going to be slightly different. We're going to get that 2H plus 2W has to come out to 100 instead of just 2H plus a single W. Where the difference now being we have this extra fenced inside here. So, right now area has 2 variables, so we can't differentiate it yet. How do we get area in terms of one variable? I'll get someone who hasn't answered. Please?
You would solve the perimeter equation for either W or H, and then plug that into the area formula.
Groovy. Sounds like a good plan to me. Which would you like to solve for?
I guess I solved for width.
Okay, I think that's what we did in the last one. So I think in this case, it's actually equally easy to solve for either one, and it's going to lead us to the same answer either way. But since you solve for width, let's solve for width. Here. So we would get 2w is 100 minus 2h. So width would be what, 50 minus h? Yeah. So what would our area function look like then if we wrote everything out in terms of h?
It would be h times 50 minus h, or 50h minus h squared.
Like that? Everybody on board so far? Alrighty. I think we're ready for to differentiate now. Is we have our area formula, the expression we want to maximize in terms of just a single variable. So if we differentiate, we'll get 50 minus 2h, which is defined everywhere, so our only critical points come when we set this equal to 0. Mackenzie, what will we get when we solve for h?
45.
Oh, what do you know? H was the same value as in the last problem. 25 what? 25 feet. And if h is 25 feet, how can we find what our width is? Benedict?
Plug it into the equation that we solved by isolating w for 1.
This one? I like it. So 50 minus h, so we'll get 50 minus 25. Surprise! Width is also 25 feet. And so if height and width are the same for our rectangle, what type of shape are we really going to get? It's a square. Fun fact, if you're given a fixed perimeter for a rectangle and you want to maximize the area, make it a square. Works like a charm. And before Rachel asks, yes, if we want to actually solve for area, I don't think the question specifically asks for it, but we would just multiply this at 25 squared, which is, I don't feel like calculating that. So now we can actually prove we found a maximum. We know that a prime of 25 is 0. All right, Zach, give me a value to the left of 25 that we can check a prime at.
1.
Wow. You picked 24.7 or something, I would have made you calculate it down. All right, so if we take a prime of 1, that'll be 50 minus 2 times 1. I think that's pretty positive. Let's see. Pietro, can you give me a value of h to the right of 25 for us to check?
24.
To the right of 20? To the right of
Right, sorry, 26.
26. I think that'll do it. A prime of 26 is 50 minus 2 times 26, which is 50 minus 52. I think that's going to be negative. And so a prime goes from being positive everywhere to the left of 25 to being negative everywhere to the right of 25. So, Hannah, what does that tell us about what's happening at h equals 25?
It's an absolute maximum.
Yeah, we have an absolute maximum. So we can say, since a prime of h is positive for all h less than 25, and a prime of h is negative for all h greater than 25, area has an absolute maximum at h equals 25. Dr. Gerstle, is it necessary for us to write out this sentence at the end? Yes. I I know you could look at this and say, oh, it goes from up to, A is going from increasing to decreasing, therefore absolute max. I want to see you write out sentences like this just so you can make it absolute clear. How does what this number line tell you actually correspond to how A of H is behaving? So since A prime is positive everywhere to the left, negative everywhere to the right, our first derivative test does tell us we have an absolute max at 25 feet. Any questions or comments on this one? Okay, let's do, yeah, we got time. Let's do one more. So this time, we're going to be looking at a slightly different scenario. I got the big chalk for this. So this time, we have to construct a box with a square base. Give me another 3D problem. Oh my gosh, my drawing skills are so bad. I don't know, that's all I've got too, not the best drawing. And it's a box whose base is a square, and we have 24 square meters of cardboard to construct the box. And the question is, how can we maximize the volume of the box? What's up, Josh?
When you say box with a square base, is that like insinuating a cube? Or could it be a square base and then like be more like rectangular?
Yeah, so when we say, good question. When we say a square base, what that means is that I would say width and length have to be the same. But height, I don't think necessarily has to. I'd say if we knew it had to be a cube, then I don't actually think we would need to do any calculus to do this one. But let's say that, I don't know, let's say that we don't necessarily know that it's going to be a cube. I mean, the final answer may or may not be a cube. So, and Avery, you're already onto something. So, yeah, what can we do? How do we come up with formulas here for stuff? I guess let's start with, let's label our variables in this picture. So what variables are we going to need to have here? Avery?
Well, normally, because it's a box, you would need base length and base width. But since we know that the width and the length are the same, we can write it as base squared.
Okay. So we know that these two should be equal to each other. So do you want to use W or L?
W.
Okay, so I'm just going to replace the length here with W, using the fact that we have a square base. And what other variable do we have in our problem? Hannah?
The height.
The height. So just like the last few examples, we have ultimately two variables for our box. We have the width of the box and the height of the box. And technically we also have the length, but since length and width have to be the same, since we're assuming our box has a square base, we only need to use W. We can use W in place of both of those variables. Or you can use length for both. It doesn't matter either way. Alrighty. What's going to be the volume of our box? That was spooky. What's going to be the volume of our box in terms of W and H? Rachel?
W squared times H.
Yeah, our volume is going to be width times length times height. And since width and length are the same here, it's going to be W squared times H. W times H. What is this 24 square meters telling us about our... Benedict, what information can we glean from this number 24 here?
We can set it equal to 2W squared plus 4WH.
2W squared plus 4WH, where did that come from?
Since we're looking for the area of all the outside, so
On the surface area.
Yeah.
Okay.
So that'll be equal to two top and bottom pieces, which are W squared, so 2W squared.
Okay, so we're going to take the area of the top and the area of the bottom, and that's going to be a W squared plus a W squared. So that'll give us a 2W squared here.
And then I was adding the four sides. We don't know if they're going to be cubes or not, so I defined each side as just WH width times height.
Yeah, so the four sides of our box are all going to have a base of W and a height of H. So each of those is going to have an area of 4WH. Or, excuse me, each of those is going to have an area of WH. And since there are four of those, we're going to add 4WH. And so I think we end up with, as Benedict suggested, 2W squared plus 4WH. Bless you, Danielle. And what should that come out to be equal to?
24.
Yeah. So it's we're given the amount of cardboard we can use to construct the box. That's going to tell us the surface area. And then, so we know that our surface area has to come out to 24 meters squared, which means now we have a volume formula, W squared times H, that we want to maximize. And I think we're going to need to use our surface area stuff in order to solve for W or H in terms of the other, so that we can get volume in terms of a single variable. So, Helen, you were asking me about this earlier. Would you like to solve for, right now I think we have a formula, 2W squared plus 4WH equals 24. And we can choose to solve that for either W or H. What would you like to solve for?
I do H because it's got less variables and you don't have to use the squared term.
Yeah, I think if we wanted to solve for W, we would end up, that would be harder because there's multiple W's showing up in this expression. We have to factor out, probably take a square root at some point. Wouldn't be very nice. But solving for H, there's only a single H, so it's probably a little easier to solve for here. All right, Helen, how do we solve for H?
So you move the 2W squared to the other side, 2 for WH, 4, and then you divide it by 4W.
Okay, so we'll get that H has to be equal to 24 minus 2W squared over 4W. Neato burrito. If we wanted to, we could simplify that out and get something like 6 over W minus W over 2, if we wanted to. Or I could leave it like this. Because now, I think we can write our volume in terms of a single variable. It's going to be W squared times this expression that Helen found, 24 minus 2W squared over 4W. What do you all think? Do you want to differentiate this as is, or should we simplify first? unless you want to do a quotient rule inside of the product rule, I would simplify this first. Well, now that I say that, that sounds like fun. Yeah. Let's simplify. What can we do to simplify this? Specifically, is there anything that cancels out nicely?
One of the W's cancels out because there's a W in the denominator.
Okay, so we can cancel these out. And I don't think anything else will cancel out too nice. I guess we could cancel out a factor of 2 from the top and bottom. But that would give us something like, what, 24W minus 2W cubed all over 4. Which is the same as 6W minus W cubed over 2. If we split this up into 2 separate fractions. Anna's on board.
Yep.
All right, Anna, what do we do with this?
Now you can differentiate it.
Now let's differentiate it. Sounds good to me. So if we differentiate, now we're in step 4 territory. What are we going to get?
6 minus 3 halves x squared.
6 minus 3 halves.
X squared. Or w squared, sorry.
I was going to say, what is this x you speak
I know,
of?
sorry, I used x.
As long as you're consistent about it, it doesn't matter really what you call your variables. As long as you're consistent. Okay, so we get 6 minus 3 halves w squared here. I agree so far. What do we do with that? Other than stare at it and marvel at its beauty.
Set it equal to 0 and solve for w.
Yeah, we find our critical points by setting the derivative equal to 0 and solving for w. Also noting there are no values of w that would make this undefined. So we'll get 6 minus 3 halves w squared is 0. It's going to tell us 3 halves w squared is 6. I'm stumped. Kinsey, where do we go from here?
Divide both sides by 3 halves.
Okay. Divide both sides by 3 halves.
4.
How'd you get 4 from taking 6 divided by 3 divided by 2?
We divide by a fraction, it becomes 6 times 2 over 3.
Ah, so dividing by 3 halves is the same as multiplying by the reciprocal. So that'll give us 12 over 3, which is 4. So w squared has to come out to 4. So what's w going to have to be if w squared is 4? Yes, when?
It's gonna have to be 2 plus or minus 2, but the negative doesn't matter because you can't have negative leaders. So
Yeah, the negative value doesn't really make sense. So we really only get one critical point that makes sense in our problem. W equals 2. I'm still going to include the negative 2 because it's going to be important in step 5, slightly. So we end up with W has to be equal to 2. That's our units. It's going to be 2 meters because our surface area was given to us in meters squared, which means width and height are all going to be measured in meters. And then if we plug back in terms of h, we'll get h equals, what, 24 minus 2w squared, which is 8 over the 8, which is going to be 16 over 8. What do you know? H also comes out to 2 meters. Yes, our box was in fact a cube, though we couldn't have known that from the start of the problem. I say it's a cube because all 3 dimensions, width, length, and height, are all end up being the same. Ugh, what's right? They're all going to end up being the same here, 2 meters. Rachel, does the question require us to find what the volume would actually turn out to be?
Yes.
Ah, so in this case, the question asks, what is the maximum volume instead of what are the dimensions that produce the maximum volume? We would actually need to go through and find what that volume is. And that's just going to be W squared times H, which is 2 squared times 2, which I think is going to come out to a volume of 8. Avery?
Meters cubed.
8 cubic meters. I think is going to be our answer here. We should also probably go through and just check to make sure we actually found a maximum. Strange noise. Strange occurrences in the building. Maybe I'm just hearing things. So we found that our volume is going to be 0 at 2 and negative 2. However, Wynn said earlier that we don't care about negative 2. And in fact, I don't think we care about any value to the left of 0, because having a negative width wouldn't really make any sense in this problem. So let's see. Riley, I need a value of W between 0 and 2 to check. What a great choice. We take V prime of 1, we'll get 6 minus 3 halves, which is going to be positive. Logan, how about a value of W to the right of 2? 3. Okay, so if we take V prime of 3, we'll get 6 minus 3 halves times 9. 3 halves times 9 is bigger than 9, so 6 minus something bigger than 9 is going to be negative. And Tyra, it seems to me like over the interval we care about, meaning for W greater than 0, it's positive everywhere to the left of 2 and negative everywhere to the right of 2. So what does that tell us? Yeah, we're going to have an absolute max. So we can say something like, for W greater than 0, if W is between 0 and 2, V prime is positive, and if W is greater than 2, V prime is negative. Thus, V of W has an absolute max at W equals 2. And I think we are done with this problem. Any questions or comments about what we did here? It's the same basic process in all cases. Yes?
Will we ever have to use the second derivative test for these?
Not for optimization, no. There is a variant you could use, like if second derivative is always positive or always negative, you could. But you don't necessarily have to. Before you pack up, I want to make a comment. I'm going to ask a question myself. Dr. Gerstle, do we need to know all these geometric formulas? Here's what I want you to know. I want you to know if I were to give you a box, like a rectangular box shape like this, how do you find the volume and how do you find the surface area? Width times height, surface area, using kind of the area of the top plus area of the bottom plus area of the sides. I expect you to know how to do that. If I give you a rectangle, I expect you to know how to find the perimeter and area of a rectangle. If I give you something fancy, like a cylinder, or a cone, or a hyperboloid, I will give you the formulas for, say, surface area and volume that you would need for something like that. So you should know kind of the more simple, like especially the rectangular type shapes. Oh, also know how to find the area and perimeter of a circle. You know all that? I'll give you anything else you would need. Have a good day, everybody. Or have a good weekend, everybody. I'll see you all on Monday.